In the video content on electrostatics, we used Coulomb's law to determine the electric field strength at any point from a charge to a point in space P. So if we've got a vector pointing from a charge to a point P, we give that a vector there, and the electric field vector was the magnitude of the charge divided by 4 pi epsilon magnitude of R12 squared, and then that points in the direction of the vector pointing from the charge to the point in space. We called that law Coulomb's law, and there's a law that's pretty similar to Coulomb's law, but it's for magnetic field strength, and the name of that law is the Biot-Savart law. And the Biot-Savart law is used to tell us the mathematical relationship between a current that is flowing and the magnetic field as measured at some point in space away from that current element. So say we've got a current of I1 amps, it's flowing in this little blue wire right here, and I want to determine the magnetic field strength at point P2 here in space. The first thing that we'll do is we'll look at an infinitesimally small element of length of the line. We'll call that DL1. And so this is just, we've taken whatever wire this is, we've made this differential length element infinitesimally small. We then are going to form a vector that points from this infinitesimally small length element to the point in space at which we're interested in determining the magnetic field strength. And so I've indicated that vector as vector R12. It's got a magnitude of R12 and a direction A hat 12. The Biot-Savart law is what we'll use to determine the magnetic field strength at that point due to this individual current element. And since it is a differential length element, we will establish what we call a differential magnetic field strength. And I'm showing here E is the symbol for electric field, H is the symbol for magnetic field. So the differential magnetic field, or the magnetic field component due simply to the current flowing through this very, very small length of wire, dH, is equal to I1, the current flowing in the line, divided by 4 pi, and then I multiply that by the length of wire that the current flows through, which is DL1. I then take that and I cross product DL1 with the unit vector pointing from DL1 to DH here, and so that's the cross product with A hat 1, 2. I'm going to divide that entire quantity by the magnitude of the vector, or how far away that this point is from the differential current element, and I'm going to square that magnitude. So the magnitude of R12 squared. So this is called the Biot-Savart law. And it looks very similar if you look at it to the Coulomb's law. We've got a constant of proportionality 4 pi. Here we had a constant of proportionality of 4 pi epsilon. We also see that magnetic field strength drops off as the square of the radial separation between the element generating the current and the magnetic field strength, which was the same as we saw here. The particle responsible for the development of the electric field strength, the magnitude of it goes in the numerator, and again what develops magnetic field is current, so the magnitude goes here. The difference is then we've got this little cross product element, DL1 cross A12, and we've got this vector cross product between the differential current element and the vector. And the reason we need to do this is because unlike in this case where the electric field strength is in the same plane as the vector pointing from the charge to the point in space, for magnetism, the vector is actually, as I've noted in this drawing with this x, it is at a right angle. It's perpendicular, it's normal, or it's orthogonal to the differential length element right here. So you can see, in this case, I've indicated that via the right-hand rule at this point, the differential magnetic field element is going to point into the page. So the problem with this realization of the Biot-Savart law here is that I only accounted for the current flowing through this differential length element. I actually need to account for, if I want to know the total magnetic field strength at this point, I have to account for the total current flowing through all of the little differential length elements. And so you should, I think, by this point, understand how we solve a problem like that. We just apply some calculus. If I want to know what total H is, H is just equal to the integral of dH, right? If I integrate along this total length of wire here, if I integrate the differential magnetic field strength, I will get the total magnetic field strength right here. And so that is equal to the integral of I1 over 4 pi dl. And I'm going to not write 1 here because there's all these little dLs now. There's an infinite number of dLs. Also, I'm not pointing from 1 to 2. I'm just pointing from this dl element to there, from this dl element to there. So this vector is going to change with the integration. So we're going to just call that a hat r, indicating that it's the vector pointing from the differential length element to the point in space that we're making the measurement. And then we need to divide that by the magnitude of these vectors, which is just going to be the magnitude of r squared, right? And r is just these vectors as we go along the path of integration. So that is an overview of the Biot-Savart law and how it applies to calculating magnetic field strength due to a current flowing in a wire.